All right, in this video, we're going to talk about, we'll begin chapter 2 dealing with limits and the derivative. The first section deals with the introduction of limits. So in this section, we'll be using the graph of a function to estimate limits and function values and use the properties of limits to find limits algebraically and find the limit of a difference quotient. All right, so in this case here, we're going to talk about just what functions and graphs are. This is just a short review of what that is. All right, now, the graph of a function is the graph of the set of all ordered pairs that satisfy the function. As an example, the following graph and table represent the function f of x equal to 2x minus 1. So here's the table of values here. We just pick x values like -2, -1, 0, 1, 2, and 3. And for each x value, we replace it in the f of x equation or put it in place of x in our f of x function. So like if x is -2, that would be 2 times -2, which would be -4, minus 1 would give us -5. For x equal -1, 2 times -1 will be -2. -2 minus 1 will be -3. If x is 0, 2 times 0 is 0, minus 1 will be -1. For x is 1, 2 times 1 will be 2, 2 minus 1 will be 1. Now for x equals 2, that'd be 2 times 2, which is 4. 4 minus 1 will be 3. And then for x equal 3, 2 times 3 will be 6. 6 minus 1 will be 5. And then you take those ordered pairs, plot them on the coordinate plane, and you should get the graph of a straight line, as you can see here. And I'm sure that they used a graphing calculator in order to graph that linear equation, f of x or y equal 2x minus 1. All right, now let's look at limits, because this is going to be the first thing we're talking about in chapter 2. Let's look at a graphical approach of finding the limit. So here, we can examine what occurs at a particular point by the limit ideas presented in the other chapter. Using the function f of x is equal to 2x minus 1, we can examine what's going to happen near x equals 2 through this chart. So what I have right here is a chart of x values that were chosen, like 1.5, 1.9, 1.99, and 1.999. Those are values to the left of 2. And then we got 2.001, 2.01, 2.1, and 2.5. Those represent the values to the right of 2. And each one of these, we're going to use f of x equals 2x minus 1 and substitute each x with these individual values here. So let me do this in the calculator. And let me clear this out. And let's suppose I want to go to y equal 2 and then clear that equation out. And then type in 2x minus 1. So I type in the 2, xt theta n for the x, and minus 1. Now here's what I'm going to do here. I'm going to press second and table set. Now, notice for the independent and the dependent, they're both highlighted at auto. I'm going to go ahead and enter these myself. So for the independent variable, which is my x variable, I'm going to highlight the word ask, because I want the calculator to ask me what values of x I want to use. So I'm going to use my right arrow key under independent and then press enter for ask. So whatever I put into the calculator for x, it will give me that value for f of x. All right, so let's go to second and graph for the table. And then that x value is just going to ask me what x values do I want to use. And these are the ones I'm going to use, which are values to the left of 2. So if I start with 1.5 and then enter, it gives me the value of 2. So for x being 1.5, f of x will be 2, based on the equation f of x equal to 2x minus 1. Then for 1.9, that gives me 2.8. Okay, now I need to move this out of the way. And then for 1.99, that would give me 2.98 for f of x. And then 1.999, I'm sorry, it'd be 2.998. All right. Now let's look at values to the right of 2, like this one, 2.001. That would give me 3.002. And then for 2.01, that would give me 3.02. For 2.1, that would be 3.2. And then for x is 2.5, that would give me 4. All right, so now let's look at what value is convergent or getting closer and closer to as we let x approach 2. Okay, so if we go in this direction, we're coming from the left. Okay, we're coming from the left. So that means here the limit as x approaches 2 from the left, as we come from the left of 2, the value of f of x is getting closer and closer to some number. It's getting closer and closer, in this case, to 3. So from the left of 2, the value of f of x gets closer and closer to 3. And let's look at this from the right, because here's the right, because 2, these values are to the right of 2. So when we get closer and closer to 2 from the right, we can write this notation, the limit as x approaches 2 from the right of the function f of x. These values of f of x are going to get closer and closer and closer to 3 as well. Okay. So we can say here, since the limit as x approaches 2 from the left of the function f of x is getting closer to 3, and the limit as x approaches 2 from the right of the function f of x gets closer and closer to 3, we can say that the limit as x approaches 2 of the function f of x is 3. Okay. So this right here leads us to the definition of what a limit is, which is on the next page. So here's how we write this. The limit as x approaches some constant of the function f of x is equal to L, or as x approaches some constant c, then f of x will be approaching some limiting value called L. And that is if the function value of f of x is close to the single real number L, whenever x is close to but not equal to c. And that's on either side of c. Okay. And also notice that I did have a plus sign and a minus sign when we were doing this limit here. Limit as x approaches 2 from the left of 2, and x and the limit as x approaches 2 from the right of 2. Those are what we call one-sided limits. So here we write this: the limit as x approaches some constant from the left of the function f of x would be k, and call k the limit from the left or left-hand limit if f of x is close to k whenever x is close to c, but to the left of c on the real number line. And then for a limit from the right, which is this right here, the limit as x approaches c from the right of f of x is going to be some value L, and we call L the limit from the right or the right-hand limit if f of x is close to L whenever x is close to c, but to the right of c on the real number line. And this is going to be very important here. So in order for a limit to exist, the limit from the left and the limit from the right must exist and be equal. So if you notice in this problem here that I just did, you see that the limit from the left of 2 of the function and the limit from the right of 2 for this function are both the same. Okay, they do exist and they're both the same. So we can say that the limit as x approaches the constant itself of that function would be that value. Okay, so now let's look at an example of this. Here's the first example. Say I want to use to graph the function f shown to estimate the function value f of negative 0.5. Well, actually, we're not finding a limit. We're just finding out the value of the function when x is equal to negative 0.5. And if you look here on this graph that's given to you, negative 0.5 is to the left of 0 and halfway between 0 and negative 1. So negative 0.5 is going to be that mark that I placed right here. And if we look at this graph, we're going to see at negative 0.5, the value of f of x has to be equal to 2. Has to be. Okay. All right. Now here's an example of a graph where we're going to be finding the limit here. And that should be parts A through D, not A through E. So here you're going to use the graph of the function f shown to estimate the indicated limits and the function value. So like in this case here, we want to find the limit as x approaches negative 1 from the left. Okay. So here the limit as x approaches negative 1 from the left. So we have to look to the left of negative 1, which is right here, and find out what's happening here as we come in from the left of negative 1. You can see here your f of x value would be equal to 2. That's because as we come from the left of negative 1, that means it's going to be equal to 2. Now, part B is the limit as x approaches negative 1 from the right. So Here's -1, we're going coming from the right of -1 coming this way. That means that your f of x value is also going to be 2. And then part C is a limit as x approaches -1. Well, if you look at the limit from the left and the limit from the right, those values are the same. So that means that the limit as x approaches -1 itself would be 2. Because notice, as I mentioned on the last page, in order for a limit to exist, the limit from the left and the limit from the right must exist and be equal. And in this case, we have that. The limit as x approaches -1 from the left is 2, and the limit as x approaches 1 from the right is 2. Okay, and I do need to correct something here because I left something off that is very important with these limit problems. That is, I left off f of x on each one of these. Okay. So the limit as x approaches -1 from the left of f of x will be 2, and the limit as x approaches -1 from the right of the function f of x is 2. That means the limit as x approaches -1 of the function f of x will also be equal to 2. Now part D is f of -1. So what's the value of the function at x is equal to -1? Well, it does exist. So here's -1 right here. The y value for that will have to be, or the f of x value has to be 2 as well. Okay. So basically, that's how we find limits here of functions. And while I'm at it, let me share something on here because you might have something where your limits may not exist, like this one. If you look at this graph right here, you have the limit as x approaches 2 from the left of f of x. If you look at -2, here's -2 right here. If you look from the left of -2, the value of f of x would be getting closer and closer to 3, as you can see. I'm sorry, 2 from the left. Here's 2. Here's 2. This is getting closer and closer to 3 here. Okay? Because from the left of 2, which is this right here, our f of x value gets closer and closer to 3. Now, for x approaches 2 from the right, the limit of that function here, we're coming from the right of 2, as you can see here. That means the value of f of x, as we let the limit approach 2 from the right, we get closer and closer to 2. Now, in part C, the limit does not exist. And the reason for that is that the limit as x approaches 2 from the left came out to be 3, and the limit as x approaches 2 from the right came out to be +2. That means these limits are going to 2 different values. So that means your limit as x approaches 2 itself does not exist. And we use the letters DNE to indicate does not exist. And then f of 2, the value of the function at x is equal to 2. Notice you have empty circles at 2. So that means the value of that function does not exist. And in part E, is it possible to define f of 2 so that the limit as x approaches 2 of the function f of x is equal to 2? Well, the answer there is obvious. Obviously, it's going to be no, because the limit as x approaches 2 of that function f of x does not exist, and the value of the function of that graph or the function at x equals 2 does not exist as well. Okay, so at least I want to show you what type of situation you might have. Okay, now let's look at the algebraic approach of finding limits. The algebraic approach. In this case here, we're going to let f and g be two functions and assume that the limit as x approaches some constant of f of x is equal to L, and the limit as x approaches some constant of g of x is equal to M. Where L and M are real numbers, both limits exist, then here's what we have. The limit as x approaches some constant of k is equal to k. In other words, the limit of a constant will always be a constant. Okay. The limit as x approaches some constant c of x will be c. So basically, it's just a direct substitution here. We just substitute the x with our constant c. So the limit as x approaches c of the function x would be c. And here we got a limit of a sum. The limit as x approaches the constant of f of x plus g of x will be equal to the limit as x approaches some constant of f of x plus the limit as x approaches some constant of g of x. That will always be equal to L plus M. And it also works for subtraction here. The limit of f of x minus g of x as x approaches some constant would be just the difference of the individual limits here. So it end up being L minus M. And then number 5 is the limit as x approaches some constant of k times f of x, where k is a constant. Here we can pull the constant out in front of the limit, so it'll be k times the limit as x approaches that constant c of f of x, which will be equal to k times that limit for any constant k. All right, next we got this. Here we got 6, 7, and 8 of theorem 2. If we have the limit of a product of two functions as x approaches some constant, then we can take the product of their individual limits. So it end up being L times M. And this also works for division as well. The limit as x approaches some constant of f of x divided by g of x. We can take the limit of the numerator over the limit of that denominator. So it'll be L divided by M, provided that M is not equal to 0. This one deals with the nth root. The limit as x approaches the constant of the nth root of the function f of x. That means we can do this, the nth root of the limit as x approaches the constant of f of x. So it'll be the nth root of L. That is, if L is greater than 0, or if your n, which is your index, is odd. And each of these properties in theorem 2 is valid for left and right limits. So those are the 8 properties of limits here that we will be using in examples like this one. Let's say I want to find the limit if it exists of this function. The limit as x approaches 2 of 5x. Now I'm going to use the property where I can take the constant of 5 and pull it out in front of the limit as x approaches 2. So this will be 5 times the limit as x approaches 2 of x. And from here I can use property number 2, where the limit as x approaches the constant of x would be that constant itself. So the 5 on the outside times the limit as x approaches 2 of x would be 2. Then multiply 5 times 2, you'll get 10. So the limit as x approaches 2 of 5x would equal 10. All right, example 4 looks like this. The limit as x approaches -2 of 8x plus 1. Well, notice I have a limit of a sum. I can write that as the sum of the individual limits, which is, of course, property number 3. So in this case here, I can write that as the limit as x approaches -2 of 8x plus the limit as x approaches -2 of 1. Now here I have a constant times some function, x, where the limit as x approaches -2. So that constant can be pulled out in front. So I have 8 times the limit as x approaches -2 of x plus, now I go ahead and bring down the limit as x approaches -2 of 1. So this will be 8 times. The limit as x approaches 2 of x will be that constant itself. So the 8 times -2 plus the limit, regardless of what this is, the limit of a constant is that constant. So the limit as x approaches -2 of 1 would just be 1. And then 8 times -2 will be -16. -16 plus 1 will be -15. So the limit as x approaches -2 of 8x plus 1 ends up being -15. Now let's take a look at example 5. In this case here, we got the limit as x approaches -9 of x squared minus 3 divided by 9 minus x. Well, here we got a limit of a quotient, which means I can write this as the limit of our numerator as x approaches -9. And that numerator, of course, is x squared minus 3 divided by the denominator, which will be the limit as x approaches -9 of 9 minus x. And of course, in the numerator and the denominator, I have the limit of the difference. Each one of them, I can write that as the difference of the individual limits. So that means I have the limit as x approaches -9 of x squared minus the limit as x approaches -9 of the constant, which is 3. I'll do the same thing in the denominator, the limit as x approaches -9 of 9 minus the limit as x approaches -9 of x. Okay. Now I can take the individual limits here. In this case here, I just replace this x with -9. So the limit as x approaches -9 of x squared will be, in this case, -9, and that's squared, minus the limit of a constant is a constant. So the limit as x approaches -9 of 3 is just going to be 3, divided by, again, the limit of a constant is that constant. So the limit as x approaches -9 of 9 is 9, minus the limit as x approaches -9 of x. I just substitute the x with -9. Now let's simplify this a bit. -9 squared is -9 times -9. That's 81 minus 3 over 9 minus a -9 is 9 plus 9, or 18. And then 81 minus 3 will be 78 over 18. And if you reduce 78 over 18, you can do this in the calculator. I'll show you that. So it'd be 78 divided by 18. Press the math key, select number 1 as a fraction, hit enter, you'll get 13 thirds. In simplest form. So that means the limit as x approaches negative 9 of x squared minus 3 divided by 9 minus x will be 13 thirds. Okay. Now, theorem number 3 is this. Limits of polynomial and rational functions here. If I have the limit as x approaches some constant of f of x, that would just be equal to f of c. So pretty much there, and that's for any polynomial function, you just do a direct substitution. But now the second one has a limit as x approaches a constant of r of x, and that's going to be equal to r of c. R is going to be a rational function with a non-zero denominator at x is equal to c. So as long as you don't, not equal to c, I'm sorry. So as long as you don't get a 0 in the denominator for a rational function, you can use direct substitution. Here's some examples of that. The limit as x approaches negative 1 of x to the 4th minus 2x plus 3. Here we got a polynomial function. We're not going to get a 0 in the denominator, so we can just use direct substitution here. So that means this will be negative 1 raised to the 4th minus 2 times x, which is negative 1, plus 3. Now, negative to an even power is going to be positive, so negative 1 raised to the 4th will be positive 1, minus 2 times a negative 1 will be plus 2, and then plus 3. So 1 plus 2 will be 3, and then 3 plus 3 is 6. So the limit as x approaches negative 1 of x to the 4th minus 2x plus 3 ends up being 6. Now part B is the limit as x approaches 2 of the square root of 3x squared minus 6. Again, with this one, we can use direct substitution. So we can just substitute our x with 2. So it'd be the square root of 3 times x, which is 2, and then squared minus 6. Well, if we square the 2, you're going to get 4. 4 times the 3 in front would be 12. So I have the square root of 12 minus 6. And 12 minus 6 will be just 6. And I'll have the square root of 6. And 6 is not a perfect square. So in this case, if the limit as x approaches 2 of the square root of 3x squared minus 6 will be just the square root of 6. And in this one, we got the limit as x approaches negative 2 of x squared divided by x squared plus 1. Well, if I replace the x with negative 2 and I square it and add 1 to it, I'm not going to get a 0 in the denominator. So this is okay. I can use direct substitution. So I'm just going to substitute my x with negative 2 in the numerator and also in the denominator. Replace that x with negative 2. So if I square the negative 2, I'm going to get 4. Because negative 2 times negative 2 would be 4. Same thing here, I'll get 4 in the denominator. And then 4 plus 1 in the denominator will be 5. So the limit as x approaches negative 2 of x squared divided by x squared plus 1 will be 4/5. I suppose we had this. The limit, given that the limit as x approaches 3 of f of x is equal to negative 8, and the limit as x approaches 3 of g of x is equal to 6, find the following limit. And that is the limit as x approaches 3 of 4 times f of x plus g of x. So now we can use some of those properties here. I can write the limit as x approaches negative 3 or 4x, but here I get that 4. Here I can pull that out in front. So it'll be 4 times the limit as x approaches 3 of f of x plus the limit as x approaches 3 of g of x. Now, we're given that the limit as x approaches 3 of f of x is equal to negative 8. So I can replace this with the negative 8 plus the limit as x approaches 3 of g of x, that's this right here, is equal to 6. So we're told what those limits are. Now let's simplify. 4 times negative 8 is negative 32. Negative 32 plus 6, negative 26. Okay. All right, now let's think about this example, because this is going to introduce us to the next thing I want to talk about. Let's say we had the limit as that we let f of x equal to x squared minus 49 divided by x plus 7 if your x value is less than 0, and x squared minus 49 divided by x minus 7. We use that if x is greater than 0. Let's say I want to find the limit as x approaches negative 7, the limit as x approaches 0, and the limit as x approaches 7. All right, if we were to use direct substitution, let's say in part A, we got x approaching negative 7 for our limit. If we were to simplify the numerator and simplify the denominator, you would get 0 over 0. And I will show you that in this example here. The limit as x approaches negative 7 of f of x. And here that value is negative 7, so we have to use this first function right here, this first expression, because our x is less than 0, and negative 7 is less than 0. Let's say I wanted to do direct substitution here. So that means negative 7 squared minus 49 in the numerator. The denominator, I have negative 7, and this should be plus 7. If I square the negative 7, I'm going to get 49. 49 minus 49 is 0. The denominator, negative 7 plus 7, is 0. Notice what I have here. The numerator and the denominator are 0. So using direct substitution here would not work because I have a 0 in the numerator and a 0 in the denominator. This is what we call, as you look at the bottom of this sheet, indeterminate form. It is important to note that there are restrictions on some of the limit properties. In particular, if the limit as x approaches your constant of r of x is equal to 0, then finding that limit as x approaches the constant of f of x divided by r of x may present difficulty since the denominator is 0. Now, if your limit as x approaches the constant of f of x is 0, and the limit as x approaches the constant of g of x is equal to 0, as I showed you in that example, then that limit of f of x divided by g of x as x approaches that constant is said to be indeterminate. And we're using that word indeterminate because the limit may or may not exist. Okay. Now on the next page, you'll see the limit of a quotient. If that limit as x approaches the constant of f of x is equal to some value of L, and L is not equal to 0, and the limit as x approaches the constant of g of x is equal to 0, then that means your limit of f of x divided by g of x as x approaches the constant does not exist. Now, this is important here. When direct substitution produces a 0 in the denominator, then replace that limit of a function with an equivalent one that can be evaluated by direct substitution. So here you're going to have to use something called factor and cancel, or factor and divide out common factors, or use conjugates. So going back to example 8, since we got a 0 over 0, we'll have to use the concept of factoring and dividing out constant terms here in this case. So let's start with part A of this problem. And that would be the limit as x approaches -7. Now, -7 is less than 0, so that means I have to use the one on the top in a piecewise function, x squared minus 49 divided by x plus 7. So that means here we need to factor the numerator, okay, if we can, because see, x squared minus 49 is the difference of two perfect squares, which I can factor into two binomials here. So here the limit as x approaches -7. Here x squared minus 49 factors into two binomials. X squared breaks up as x and x. 49 is a perfect square because 7 multiplied by 7 gives you 49. And since it's a difference of two perfect squares, one must be plus, the other one must be minus. And all that's divided by x plus 7. So now we got x plus 7 in the numerator and the denominator. We can divide that out. So we will simplify this as the limit as x approaches -7 of the quantity x minus 7. Now we can apply direct substitution by replacing the x with -7, because we won't get a 0 in the denominator because of its simplification here. So here -7 minus 7 ends up -14. So the limit as x approaches -7 of x squared minus 49 divided by x plus 7 will end up being -14. So that's part A. Now part B is the limit as x approaches 0 of f of x. Now, our x value is 0. Is there an expression for x equal to 0? In this case, there isn't. It's for x. This one is for x is less than 0, and this one is for x is greater than 0. There's no expression for x is equal to 0. So its limit as x approaches 0 of the function f of x does not exist. Or you can abbreviate this as DNE, does not exist. All right, and in part C is the limit as x approaches 7 of f of x. In this case here, the value that we're going to, or the constant that we're going to, is 7. And 7 is positive. That's greater than 0. So we have to use this expression of x squared minus 49 divided by x minus 7. Now, of course, if you substitute your x values with 7, you're going to get 0 over 0 as well. So that's an indeterminate form. So here we have to factor and divide out our common factors here. So that x squared minus 49, if you recall, back in part A, factors as x plus 7 times x minus 7. And that's going to be divided by x minus 7. But this time, x minus 7 is in the numerator, and the denominator, we can divide that out. We'll be left with the limit as x approaches 7 of x plus 7. Now we can just do direct substitution here. So replacing the x with 7, you're going to get 7 plus 7, which is 14. So the limit as x approaches 7 of f of x, or the limit as x approaches 7 of x squared minus 49 divided by 7, divided by x minus 7 will be 14. Okay. So with this example, we came up with indeterminate forms here for parts A and B. I mean, A and C. Part B, the limit did not exist because there was no expression for x is equal to 0. All right, look at example 9. A and B. This one does have something to do with direct substitution. Well, not direct substitution. Indeterminate forms here. In this case here, we have the limit as x approaches negative 3 of x squared plus 4x plus 3 divided by x plus 3. Now, of course, if you replace the x in the numerator with negative 3, you'll get a 0 in the numerator. And of course, obviously, if you replace the x with negative 3 in your denominator, you'll also get a 0. So we have 0 over 0, which is our indeterminate form. So that means we're going to have to factor and divide out common factors in this case. So let's see if we can factor. I'm going to bring over the limit as x approaches negative 3. That x squared plus 4x plus 3, I can factor this into two binomials. X squared breaks up as x and x. And then factors of 3 that gives me 4x as a middle term will have to be a plus 3 and a plus 1. And that'll be divided by x plus 3. Then the next step would be divide out your x plus 3. You'll end up with a limit as x approaches negative 3 of the quantity x plus 1. And now we can do our direct substitution here. Replace that x with negative 3, so it'll be negative 3 plus 1, which is negative 2. So the limit of x squared plus 4x plus 3 divided by x plus 3 when x approaches negative 3 ends up being negative 2. All right, and part B is the limit as x approaches negative 8 of x squared minus 64 divided by x plus 8. Again, if you replace the x with negative 8 in the numerator and the denominator, you will get 0 over 0, indeterminate form. So again, we'll have to factor and divide out constant terms here. So let's do that. The limit as x approaches negative 8. If we factor x squared minus 64, that's a difference of two perfect squares. X squared will be x and then x. 64 is a perfect square because 8 times 8 gives us 64. Now, one has to be plus, the other one has to be minus. All that's divided by x plus 8. And you can see that x plus 8 divides out. That'd be equal to the limit as x approaches negative 8 of x minus 8. Replace your x with negative 8 because you're not going to get a 0 in the denominator. So it'll be negative 8 minus 8, or negative 16. Okay. Now keep in mind, the only calculus that I've done here is just taking the limits. Everything else is just algebra. And I will caution you, if you're not good at factoring polynomials in this case, I do have a playlist that I've posted in the Getting Started menu in Canvas called College Algebra Resources. Go ahead and click on that and you'll be taken to a playlist of YouTube videos that deals with factoring. Okay, so please watch those videos as much as you can. All right, next we'll look at the limit of difference quotients. Limit of difference quotients. Let's say we let the function f be defined in an open interval containing the number a. One of the most important limits in calculus is the limit of the difference quotient. And here is that limit of that difference quotient here. The limit as h approaches 0 of f of a plus h minus f of x divided by h. Now keep in mind, when we get into talking about the derivative or introducing you to the derivative, we're going to be dealing with this difference quotient. And if the limit as h approaches 0 of the quantity f of a plus h minus f of a is equal to 0, as it often does, then that limit is going to be in an indeterminate form. So in some cases, you may have to simplify a bit by doing some factoring if at all possible, or you might have to use conjugates. All right, take a look at this example number 10. Let me bring this down. Here I want to find the limit as h approaches 0 of f of 1 plus h minus f of 1 divided by h if the function f of x is equal to 2x minus 1. Okay. So here's the first thing I'm going to do here. I'm going to evaluate this part right here, f of 1 plus h. My f of x function is 2x minus 1, so for that x is going to be replaced with what's inside the parentheses of the f, 1 plus h. So it'll be 2 times, and in parentheses, 1 plus h, and then bring down the minus 1. Now, when I simplify that, it will be this. If I distribute the 2 over the 1 plus h, it will be 2 plus 2h minus 1. And then 2 minus 1 will be 1 plus 2h. And also, I'm going to evaluate f of 1, which is this part right here, after the minus sign. So I just simply replace the x in f of x with the 1, so it'll be 2 times 1 minus 1. Well, 2 times 1 will be 2. 2 minus 1 will be 1. So f of 1 will be 1. Now, here's what I'm going to do here. Subtract these two. Because that numerator, if you look at it, is this. F of 1 plus h minus f of 1. This is our numerator. And f of 1 plus h is this, 1 plus 2h from step number 1, minus f of 1 turned out to be 1. All right, if I simplify this, the 1 minus 1, that's 0, that's gone. So I'm left with just simply 2h. Now I'm going to write step number 3, which is that f of 1 plus h minus f of 1. That difference will be divided by h. Well, f of 1 plus h minus f of 1 turned out to be 2h. So 2h will be divided by h. And here the h's divide out. I'll be left with just 2. Then the final step here is the limit. I'll take the limit as h approaches 0 of that expression, f of 1 plus h minus f of 1, all divided by h. Well, that ended up being 2, so the limit as h approaches 0 of 2. And one of the properties for limits is that the limit of a constant is the constant. So the limit as h approaches 0 of 2, excuse me, is equal to 2. Okay. So if f of x is equal to 2x minus 1, then the limit as h approaches 0 of f of the quantity of 1 plus h minus f of 1 divided by h ends up being 2. Okay. All right, let's look at example 11 on your handout. Is this. Here we got the limit as h approaches 0 of f of 7 plus h minus f of 7 divided by h. If our function f of x is equal to x squared plus h. All right. So the first step is find f of 7 plus h. If f of x is x squared plus 8, then we just replace the x with that 7 plus h. So it will be 7 plus h quantity square plus 8. Now, off to the side, I'm going to do 7 plus h quantity square. I'm sorry, 7 plus h quantity square. That's what I mean. Now, since 7 plus h is used as a factor twice, I'll just write 7 plus h times 7 plus h, and then apply the FOIL method. That means I do the first term times the first term, 7 times 7, that's 49. The outer will be 7 times h will be plus 7h. The inner will be h times the 7 will be plus 7h. And then the last times the last, h times h will be h squared. And then we just simplify this. I will write down the 49. 7h plus 7h will be 14h plus h squared. So that's what 7 plus h quantity squared ends up being, which will be, in this case, 49 plus 14h plus h squared. And I'm going to bring down that plus 8. And then when I combine like terms, 49 plus 8 will be 57. So I have 57 plus 14h plus h squared. So that's what f of 7 plus h will be. Now for the f of 7, which is this right here. Well, f of x is x squared plus 8, so I'll just replace the x. X squared plus 8 will replace the x with that 7. So it's going to be 7 squared plus 8. 7 squared is 7 times 7, that's 49. 49 plus 8 ends up being 57. All right, now step number 2 is do the numerator, which is f of 7 plus h minus f of 7. That's this numerator up here. Now, f of 7 plus h, we found that out to be 57 plus 14h plus h squared minus f of 7, that was 57. You're going to see if I do 57 minus 57, that's 0, that's gone. I'll be left with just 14 h plus h squared. Okay. And now step number 3, I'll take my f of 7 plus h minus f of 7, whatever I got for that, it'll be divided by h. So f of 7 plus h minus the f of 7 was this, 14h plus h squared. That will be divided by h. And I could factor out the h in the numerator, but since I only got just one term in the denominator, I can take each of these terms in the numerator and divide that by that one single term. So I can write this as 14h divided by h plus h squared divided by h. You're going to see that the h's divide out here, and h squared divided by h will just be h. So this is just 14 plus h. Okay. As you can see here, this h divides out with an h and h squared, leaving me with an h in the numerator. So it'll be 14 plus h. And then number 4 is to take the limit. So it's a limit as h approaches 0. Limit as h approaches 0 of this. But that turned out to be 14 plus h, so we have the limit as h approaches 0 of 14 plus h. Well, here we have an algebraic expression, or a polynomial expression. So we can use direct substitution here. So I can substitute the h with 0, so it'll be 14 plus 0, because h is getting closer and closer to 0, so 14 plus 0 ends up being 14. Okay. So the limit as h approaches 0 of f of the quantity 7 plus h minus f of 7 divided by h, if your function f of x was x squared plus h, would end up being 14. All right, and finally, this last example in this video, let's say you had f of x equal to the square root of x. Now, this is one of those examples where you have to use the conjugate, which I'm going to explain shortly. F of x equal to the square root of x, you want to find the limit as h approaches 0 of f of 3 plus h minus, f of 3. All right, so number 1, let's find f of 3 plus h, and also we're going to find f of 3. Well, f of x is the square root of x. So we replace the x with that 3 plus h. So the f of 3 plus h is going to be equal to the square root of 3 plus h. And of course, for the f of 3, f of x is equal to the square root of x. So that means I'll just replace the x with 3. So f of 3 is equal to the square root of 3. All right, step number 2 is subtracting f of 3 plus h minus f of 3. Well, f of 3 plus h is the square root of 3 plus h minus f of 3 is the square root of 3. And that's all step 2 is. Now, step number 3, we're going to take that expression in step number 2, f of 3 plus h minus f of 3, and divide that by h. Well, f of 3 plus h was the square root of 3 plus h, minus f of 3 is the square root of 3. That would be divided by h. Now, in this case here, we're not going to get much done with this unless we use what they call the conjugate. Okay. So if I have a conjugate, let's say A plus B, its conjugate is just simply this. The terms are the same, but the operation symbol changes to the opposite. So the conjugate of A plus B will be A minus B. And for A minus B, its conjugate would be A plus B. So all you're doing there is just switching the signs. So for this one, the square root of 3 plus h minus the square root of 3, its conjugate would be the square root of 3 plus, the square root of 3 plus h plus the square root of 3. So what I'm going to do here is multiply the numerator and the denominator by its conjugate. That's the square root of 3 plus h. This minus sign would change to a plus. I'm going to do the same thing in the denominator, square root of 3 plus h plus square root of 3. All right, in this case here, notice I'm putting these in parentheses because I have to use the FOIL method for this one. And you're going to see why. The first term times the first term, that's the square root of 3 plus h times itself, which is actually the square root of 3 plus h squared. If you take the square root of something and you square it, it eliminates the radical. So you'll be left with just the 3 plus h. That's the first term times the first term. The outer is going to be these two terms put together. And it's going to be plus the square root of 3 times the square root of 3 plus h. That's the outer. The inner is these two right here put together with a minus sign. So it'll be minus square root of 3 times the square root of 3 plus h. And then a minus times that plus would be minus the square root of 3 times itself, which is actually the square root of 3. And that's going to be squared. That's just going to be 3. Reason being is because if you take the square root of something, you turn around and square it, it's going to be left with what's underneath that radical. The square of the square root eliminates the radical. Now my denominator, I'll just have to rewrite this as h in the denominator times, and in parentheses, the square root of 3 plus h plus the square root of 3. Now let's simplify this numerator. You're going to see that these two middle terms right here, the square root of 3 times 3 plus h and minus square root of 3 times 3, the square root of 3 plus h, that's gone. And I might as well say this, that 3 minus 3, that's 0, that's gone as well. All you're going to be left with is just the h. So it's going to be h divided by h times the square root of 3 plus h plus the square root of 3. And notice something else, your h's divide out as well. So you'll be left with, in this case here, a 1 in the numerator divided by the square root of 3 plus h plus the square root of 3. So all of this was step number 3. All right, now step number 4 is taking the limit as h approaches 0. So the limit as h approaches 0 of this right here, f, and I'll just rewrite it as f of 3 plus h minus f of 3 divided by h, which is this right here. So in this case here, I'll write this as a limit as h approaches 0 of 1 over the square root of 3 plus h plus the square root of 3. And now I can go ahead and take that limit. Okay. So as h approaches 0, the square root of 3 plus h, that h goes to 0. So I'm left with 1 over the square root of 3. And then I got another square root of 3. Now, how many square roots of 3 do I have? 2 of them. So it'd be 1 over 2 square root of 3. Okay. And notice I brought that notation of the limit as h approaches 0 over each time. I have to keep doing that until I actually take the limit. Okay. So the limit as h approaches 0 of f of 3 plus h minus f of 3 divided by h, when f of x is equal to the square root of x, ends up being 1 over 2 square root of 3. Okay. All right, so do get some practice over this here, because you're going to be seeing a lot of this when we go into one of the sections when we introduce the definition of a derivative. Okay, so that does conclude this video on section 2.1, which is the introduction to limits. Feel free to reach out to me if you have any questions about any of the homework problems in my math lab or any of the problems that were discussed in this video for this section.